So far we have covered in this lecture the minimization of the loss function corresponding to L2 norm regularized least square problem, and the solution, the loss function for the L2 norm regularized least squares is given by this. This is a loss function, and the solution, we saw that the closed form solution, since now we understand that this function is convex, and that's why minimization of this function with respect to W will give us the optimum solution, which happens to be the global minimizer of the loss function. And the closed form solution is W star is equal to phi transpose phi plus lambda times I, where I is an identity matrix inverse, times phi transpose times Y. This is a closed form solution. We also saw that if we want to use a gradient descent algorithm, then the update equation is W nu is equals to old W plus alpha, which is the learning rate, times Y minus phi of x transpose times W times psi of x minus lambda times W. So the effect of L2 regulation is that with every update, as you can see here, the magnitude of W will keep on decreasing, where this lambda is greater than 0. Lambda is greater than 0, and the alpha is some small learning rate for our gradient descent algorithm. And this is online gradient descent algorithm, where the weight vector W is updated based on the every input data sample. The L1 norm regularized least square has the following loss function, which is the L2 norm of the loss over the L2 norm of the errors, L2 norm of the error vector, or the sum of the square of the errors, plus lambda times L1 norm of W. And as we have as we know, this L1 norm is not differentiable at W equal to 0, when the vector W or any component of W is equal to 0. So W is a vector, it's an n-dimensional real vector, and whenever any component of W is equal to 0, then the objective function is not differentiable. At that point. But as we have studied in the previous lecture, we saw that we can use subgradients instead of a gradient, and then we can have a subgradient descent algorithm. Subgradient descent algorithm. Right. And later on we will see what the update equation is, how we can compute the subgradient of this term. So there are various ways to optimize to sort of like minimize this loss function. So W star is equal to arg min over W norm L2 norm of Y minus phi times W, L2 norm squared, plus lambda times norm of W1. So now the goal is to minimize this loss function, that is minimize with respect to W, norm of phi times Y minus W plus lambda times norm of W1. There are various ways to solve this optimization problem. Now we understand that this objective function is convex. Since any norm is convex, so this is the sum of convex functions, and that's why it is convex. And the domain of this function is W, the entire n-dimensional real space. So this is the convex optimization problem. And then there are various algorithms. Number one, we can use, for example, a normal subgradient descent algorithm. Subgradient descent algorithm. But we will. It would be an assignment for you to show that if you implement the naive subgradient descent algorithm, it would be very slow. the rate of convergence is linear. So it turns out that this algorithm is very slow. There are various other ways for example, we can convert this. So this is an unconstrained optimization problem. It means that there is no constraint on the learnable on the parameter w, which is an optimization parameter over which we are minimizing this objective function. So this is an unconstrained optimization problem. It turns out we can convert it into a constrained optimization problem. And use various algorithms in the convex optimization literature. To solve this problem, we can use various second order methods. For example, we can also use interior point methods. Interior point methods to optimize this. But then there's one special algorithm invented to discovered to solve this one particular optimization problem, which is known as iterative soft thresholding algorithm, or ISTA. So for the purpose of interior point methods, it's way too complex to explain in this machine learning course. This is not a comprehensive course in convex optimization, and we are not going to discuss the formulation. This formulation will come when we discuss the SVM. So in this particular lecture, first we will study the ISTA algorithm, and then we will consider the subgradient descent algorithm. So these are the two algorithms that we are going to use to minimize this loss function. In order to solve this convex optimization problem. And the subgradient descent algorithm follows naturally. I mean, we can just compute the subgradient of the term norm of W1, and it becomes this very simple algorithm to sort of implement, as well as the derivation of the update rule is also very simple. Iterative soft thresholding algorithm, on the other hand, we can give you just a pseudocode. We can just give you pseudocode to implement this. And for those who are interested, for example, one day if you want to develop your own optimization algorithm, for example, if you know anything about deep learning, there's a high chance that you might have heard of algorithms like RMS prop, Adam optimizer, and various other algorithms, right? So one day, suppose if you want to invent an optimization algorithm of your own, perhaps it would be better to understand how do we derive this algorithm, right? So we will see the complete derivation of this algorithm, so that you will have much clearer understanding as to how do these optimization problems are actually solved in practice. And one day, if you feel that perhaps ISTA is not sufficient enough, for example, if it's not fast enough, then perhaps you can develop a better algorithm. And in fact, better algorithms have been developed. For example, there's a modification of it which is known as fast ISTA, or in short FISTA, which you can go on the internet, read several research papers. So we will cover the complete derivation of the ISTA algorithm, and then perhaps you can, if you are more interested, you can see the derivation and you can read the original research by the authors as to what's the motivation behind developing this ISTA algorithm. So now let's see how to derive the update equations for the L1 norm minimization. And also, while we're doing this, we'll have a very interesting result actually, which shows how can we design a better algorithm for minimizing the least square objective function when we have to use the entire data set as a whole. So the normal equation asks you to invert the matrix phi transpose times phi, which may not be invertible. Even when if it is invertible, it is computationally very exhaustive to invert very large matrices. So we will see a nice you can say update equation that avoids that inversion and has a nice multiplication of matrices instead of inversion of matrices. So let's see what actually this ISTA algorithm is and how can we derive the update equations for the parameter W to obtain the global minimizer of this loss function.